You know, so it's the concept. You need to know some important concept. Now, as far as the equations, formulas are concerned, you can write down on a piece of paper, right? Yeah, it's like a cheat sheet you like. This way, you can find a formula more quickly. Just save some time. Okay, so let me finish this example first, and then I will talk about the exam, and then if you have any questions, I can answer. Huh? Okay. Good. So this was one of the exam problems I gave in the past. Yeah, this one. Okay. Okay, I give you some time to draw the circuit. Let me give you all the known parameters.
Is the top left one supposed to be R1 too?
R.
Because like there's already an R21 on the bottom, right?
Let me see. R21, R22, R12. Yeah.
Okay.
Yeah. You know, you can call anything you like, right? It doesn't matter. Yeah.
Don't confuse it.
Yes. Good. Okay, so these are the known parameters. This one is known. It's 3K. Okay, so that's all we know. And then I know that A sub I overall is minus 400. A sub B overall is minus 20. And the Q point of first stage is located in the middle of DC low line. Okay. So we need to find the values of RE1, R12, R22. Right? And then maybe we can do the can sketch the DC and the AC low lines of the second stage. Okay. Now, Oh, beta. This is called beta 2. Okay, this is beta 1. So this is 100. This is 200. So that was one of the exam problems. Looks good? Huh? Bad?
It's like the last problem almost of the homework.
The last, yeah. Okay. Now, this type of problem is called a design problem because some of the components in the circuits are not known. Okay. Typically, the design problems are less straightforward than the analysis problem. Now, analysis problem means you have all the components, you just have to calculate A sub I, A sub B, everything. Okay? So if I were you, I would prefer to see the analysis problem, not the design problem. Okay? But nonetheless, the concepts are the same. Okay? So basically, you need to, when you have a problem, okay, you need to first look carefully about all the information you have, right? Okay, so you can see that this is a two-stage amplifier, yes? And then you look at the second stage. All the components are known. So that means you can do the DC analysis, you can do the AC analysis of the second stage right away, right? Okay, so therefore the concept, the approach is the following. You can try to find AI2, AV2 of the second stage, right? So that's the first step. Then, because the overall are known, so from here you can find out what? AI1 and AV1, correct? Because this is the product of AI1 and AI2. So then, hopefully, with these two information, you're going to have two equations, correct? And hopefully, you have you have the same number of equations and the same numbers of unknowns. Now you say, okay, well, there's three unknowns, right? I can end up with two equations. I still need one more equation. Well, that equation probably will be coming from here. Huh? Because the Q point of the first stage is known. So this is this approach. Okay? So let's go ahead and do that. So I'm going to go from the second stage, yes? And I'm going to have to do the DC first, yes? Right, so that is ICQ2, IDQ2, this is BCEQ2, right? We have done this many times. Okay, so you go around the input loop, right? The input loop, and you use KVL. You get the equation. VTH2 equal to IBQ2 RTH2 plus VBER, right? Plus ICQ2 RE2 plus RE2 prime. Correct? And ICQ2 is beta 2 IBQ2. And the formula for VTH2, remember, right? VCC times R22 plus R21 and R21 on top, right? So I have the number here. Sometimes my number could be incorrect. correct. So you have to double check yourself, okay? 2.5. Yeah, it's 2.5 volts. And RTH2 is the parallel of two resistors, yes? So that is 2.5K. All right, so you put this value here, you can solve for IBQ2, right? And that is 17.6 microamp. So therefore, ICQ2 is beta times that, right? So it's 1.76 milliamp. Now you also have to try to find BCEQ2, huh? So if you go to the output loop, BCC equal to BCEQ2 plus ICQ2 times RE2 plus RE2 prime, right? So this is the KVL of the output loop. So therefore, from here you can calculate BCEQ2, and that is equal to about 13 volts. This is 15, right? Yeah.
And it would be a ICEQ, but they're essentially equal, right? ICEQ.
Yeah, I said that many times, okay?
Essentially.
Yeah. Make sure you don't ask me this question again, right? Okay. So this can be assumed as ICEQ2. Yeah. Okay. So that is the DC analysis of the second stage. Now I can go to the AC analysis, right? And the first thing to do is to draw the equivalent circuit, all right? And again, if you make a mistake on the equivalent circuit, you know what? Everything else will be wrong. And that is a major mistake, by the way. Yeah? Because if this is wrong, everything is wrong. What can I do for you? You know? So you have to be careful, huh? This must be correct. If this is wrong, I can easily take off 10 or 20 points, right? Okay, so that's the input terminals of the second stage. We call this IN2, right? And this one is R22 in parallel is R21, correct? And that is the base terminal. And then the emitter is connected to RE2 to the ground. Yes? Now, again, don't make a mistake here because this capacitor is short under the AC condition. So therefore, RE2 prime is gone. Yes? Now, I don't know how many times I can emphasize that, but I'm going to still see somebody making mistake in the exam. Okay? Hopefully this semester is different. And the collector, what's the collector? The collector is connected to the ground, right? Connected to the ground. That's it, right? Okay, and where's the output terminal? Right here, right? VO, I can call VO2 if I like. Okay, then the model R pi 2 beta 2 IB2, right? That's IB2. So that's it.
So the collector is connected to ground?
Yeah, why not?
For this.
Again, you need to know what is the meaning of that symbol, right? That is the positive polarity of the DC battery. So, and the negative is connected to the ground. Okay, that's what it means. And under the AC condition, the battery is always a short circuit.
When you have a problem where you have a positive voltage at the top and a negative at the bottom, can you just move it to the top and then you put in a positive voltage? So you have a plus 9 on top and a minus 9 on
Are you
bottom.
talking about an AC or DC condition?
DC.
For the DC condition, you cannot just move in top. Okay, I did an example in the class. Remember? I did an example in the class that has a voltage on the top, a voltage on the bottom. And I went through the DC, I went through the AC analysis. Actually, for the AC, it's the same, right? Top is ground, bottom is ground. But for the DC, it's different. So you need to go through that example. I don't have time to do that. Okay. Yeah. I barely have time to finish this example. And I still have to tell you about the exam, unless you don't want to hear it. Okay, I assume so. Okay. Now there's a component in the circuit you have to calculate, which is what? R2, right? And the formula for R2 is VT beta over ICP, right? Okay, so I have 1.5K for R2. All right, so now VO2 is equal to, there are two currents, huh? Right? But this current is smaller than that, so it's beta 2 IB2 times RE2. Yes? Okay. And V into is, this voltage is that, right? It's R pi 2 IB2 plus that, which is beta 2 IB2 RE2. So you take the ratio, AB2 is equal to, because IB2, IB2 will cancel, right? So it's beta 2 RE2 over R pi 2 plus beta 2 RE2. So therefore I can calculate the value of that, and it's 0.97. By the way, you need to recognize that this, the second stage, is a common collector amplifier. Huh? And when you have a common collector amplifier, A sub V is always smaller than 1. Okay? So at the end, if you get the value of A sub V to be larger than 1, then you know something is wrong. You need to go back. For the common emitter, if you look at the circuit again, the first stage is the common emitter. For the common emitter, the A sub V is always larger than 1. Okay? Okay, now let me try to find out what is A sub I2. Okay, so this is I2, right? And that's what we call I sub L2. Okay, so A sub I2 is this ratio of 2, right? So I sub L2 is simply what? Beta 2 IB2, correct? This current actually is the sum of 2, but again, this one's smaller than that, right? Okay, and what is I2? I2? IB2 is a portion of IN2, correct? By what we call the current divider rule. And if you look into these two terminals, the equivalent circuit, I'm going to call this I into prime, right? So you have one branch that is I into prime. You have the other branch, which is the parallel of this two resistors, right? So therefore, you can use the current divider rule. So you have R into prime plus R22 in parallel is R21, and then R22 on the top. Why is it? They make it too loud, the sound. Okay, so from here, okay, you go from here, okay? Go on here. I can rearrange the equation so that I have I into equals I_2 times R22 equals R21, and then Ri into prime plus R22 equals R21. You know, I did this last time. Very similar, right? Yeah. Okay. Therefore, now I can take the ratio. So AI2 is the ratio of IL2 over I in 2, correct? So if I take the ratio, this is IL2 right here, right? So it's beta 2 divided by that. So this is R22 imperial is R21, right? Over I into prime plus now what is I into prime? I told you the shortcut, right? What is it? Is this plus this multiplied to the weighting factor, right? So it's R pi 2 plus the weighting factor, which is beta 2, and then RE2, right? Okay. So with that, I can find out my AI2, right? So AI2, the value for AI2 is 4.6. So this is all I can do for the second stage. Yeah? Or maybe I can do one more thing. I need to find out what is the input resistance of the second stage. It is what? It is R22 in parallel with R21 in parallel with RIN2 prime, correct? I'm talking about here. Right? Here, it's called IN2, right? And that is equal to 2.4K. Okay, so now I can go to the first stage.
That becomes the load for that.
Yes, that becomes the low. So I'm going to try to find out what are the expressions of AI1 and AV1. Yes? And by the way, I know the values of that. So what is AI1, by the way? Is AI overall minus 400 divided by AI2, which is 4.6, correct? So it's minus 87. And I also know AV1, which is minus 20 over 0.97, correct? So I got minus 21. Okay, I can erase that, okay? Okay, now, so if you look at the first stage under the AC condition, R1, 2 imperial is R1, 1, yes? That is the base terminal. That is the emitter connected to RE1 to the ground, yes? That is the collector connect to RC1 to the ground. And we have to also put a load, which is RIN2, right? So the load is the input resistance of the second stage. Correct?
You don't have to do DC analysis first.
You cannot,
You cannot.
because you do not know the values of those resistors. So this is VO1, right? Okay, and here's the model of the BJT. Beta 1, IB1, IB1, RI1, right? Okay, so what is AB1? I'm going to do this more quickly, okay? You should know that these two are in parallel, correct? So then multiply to the current, so it's minus beta 1, IB1, the parallel of RC1 and the RN2, yes? So the top is what? VO1, correct? What about the bottom? Bottom is this. This is equal to that plus that, yes? So it's R pi 1 IB1 plus beta 1 IB1 RE1. So the bottom is VI1, correct? Okay, so IB will cancel, right? So you get minus beta 1 RC1 in parallel with RN2 divided by R pi 1 plus beta 1 RE1. Hopefully I have one unknown in the equation. Because this value is known, right? It's minus 21. Well, unfortunately, I do not have one unknown. I have two unknowns, right? Yeah, this is not known. This is not known. But typically, we can use the following assumption. Okay, we can assume that R pi 1 is much less than beta 1 RE1. Why can I do that? Because beta is a large number, right? So if you multiply these two, that will be typically larger than R pi 1. So I can make the assumption, and then I can come back to verify the assumption later. Yes? Okay, so I'm going to do that. Therefore, I have only one unknown, which is RE1, right? And that is about 65 volts. Okay, now let me try to find out what is AI1. Okay? So AI1 is, we call this IL1, right? It's IL1 divided by, this is II1, yes? Okay, we have done this many times, okay? So IL1 is a portion of that. So it's minus beta 1 IB1, right? And then use the current divider rule. Yes? So the top is IL1, got it? This, again, it's nothing but the current divider rule. Yeah? This is the main current, right? And then this is the division. Okay. The lower one is a little bit trickier, but we have done that many times, right? So this is, I'm going to call this as my R in 1 prime, right? So if I remember, it's just like the second stage, huh? What was it? So it will be IB1 times, yeah, R1, 2 imperial is R1, 1, and then R1, 2 imperial is R1, 1 plus R in 1 prime. I think that is the correct expression for this is I1. Again, it's almost the same as the second stage. Huh? You can double check. Okay, so IB and IB cancel, right? What is the unknown? Huh? Okay, this is known, right? No. That's known, correct? This is not known. Huh? Not known, right? What about this? Huh? R in 2 prime is equal to R pi 1 plus the weighting factor times RE2, right?
So you still assume that that one is very small?
Yeah. So again, if I assume this is smaller than that, right, then I would have one unknown. And the unknown is what? Correct? That is the unknown. And that unknown is about 50K, according to my notes. But we have not solved the problem yet, right? I found the parallel combination of 2, but I need to find the individual values of the 2. So now I would have to go to the the BC analysis to try to figure out. Okay, so now I have to go to the BC analysis. Hopefully I can figure out what are the individual values of the 2 resistors. Okay, so RPH1, EPH1, right? RE1, RC1, VCC, right? So that's the first stage under the BC condition. And this is IBQ1. This is ICQ1. So BCQ1, right? Okay. Fortunately, I have a very useful information right here. So that means my BCQ must be equal to what? Half of VCC. So it's a 7.5 volts. And then you use the output loop, right? So VCC equal to ICQ1, RC1 plus VCQ1 plus ICQ1, RE1. Right? This is the KVL of the output loop. And this is what we want to know, right? Because this is known. So the only unknown is ICQ1. So we can find that. So ICQ1 will be about 2.4 milliamp. Okay, now I can go to the input loop. Right? So VTH1 equal to IBQ1 RTH1 plus 0.70 plus ICQ1 RE1. This is known, right? Oh no, it's not. VTH1 is VCC times R what? 12 plus R11 and R11, right? So that's not known. Equal to, hopefully on the right hand side is known. Huh? Is it known on the right hand side?
Yeah.
No, right? Everything is known. So on the right hand side, I can find out the value, which is 1.44 volts. So now if you focus on this equation right here, right? This 1.44 comes from here, okay? That is 1.44, okay? Now, as you know, what do I do next? I'm going to have to play a trick, right? Yes? I'm going to multiply R12 on the carbon on the bottom. And therefore, this is the parallel, right? Correct? And that is equal to 1.44 volts. So this is known, right? So therefore, I can find out what is R11, 55K, R21, 516K. Okay, so let's figure out the low lines. So let's figure out what are the low lines of the second stage. Yeah? Okay. So this is IC2, VCE2, right? Because the second stage. So the PC low line will be somewhere here. And the two boundaries are VCC, which is 15 volt, right? And this one is VCC over RDC. Yeah? And what is that? What is RDC? Yeah, I go from the top to the bottom on the DC condition. This is open, right? So it's 1K. So 1K, 15 divided by 1K, what do you get? You get 15 milliamp. Yes? So that's the boundary condition of the y-axis, right? And where's the Q point?
The middle.
No. The middle is the first stage.
Oh, first stage.
Yeah,
sorry.
yeah. We're talking about the second stage, and we have calculated ICQ2, which was 1.8. Is it? Okay, 1.8. Oh, so that 2 points are located very low. Yes, somewhere here. that's ICQ2 1.76 milliamp, right? So, and this is BCEQ2, that's about 13 volts. Now, by the way, the Q point must be located within the on the DC load line. Yes, it cannot go outside. So therefore, if you look at the current, the maximum current can have for the circuit is what?
15
Yeah,
milliamps, yeah.
that is the maximum current can have. Okay. So if you have a question, say, okay, you have to place the Q point within the DC operation region, then you know that the maximum current can have, the maximum collector current can have is that. Yes? Cannot go outside. Okay. Then let's find out what is the, so the slope is minus 1 over R DC, right? Which is minus 1 over 1,000. Okay, then let's do the AC load line, right? So the AC load line has to go through the same Q point, but with a different slope. So what is RAC? It's 500, right? Because if you look at the output loop under the AC condition, this is short, right? So all you have is just the 500. Okay, and the boundaries, we call this IC prime. We call this VCE prime, correct? So what is IC prime? I gave you the formula before. IC prime is equal to ICQ plus VCEQ over RAC. Okay, so that's the formula. So therefore, is 1.76 milliamp plus 15 volt divided by 500. Yes? So what do you get? This is 30 milli. This is 30, right?
30.
Wow, 31.76 milliamp. So this design is not too good. Anyway, so this is about 31 milliamp. Yes. Now you should also double check your answer because that value must be larger than that. Correct? If you have a value that's less than that, then you know that's a mistake. Now,
BCEQ is 15 and not 13.
huh?
The BCEQ.
Oh, VCEQ. Oh, yeah, I'm sorry. So this is 13, right? Okay, 13. Well, so I would say, anyway, it was 31, yeah? Okay, then. So basically, if you have a small signal, what does he do? So that's the Q point, right? That's the AC load line. It's the DC load line. So basically, that's the Q point, right? So that will become the upper bound of the swing. That will become the lower bound of the swing. Yes, and the swing will be centering at the Q point, right? Like that. But if you want to get a maximum undistorted swing, then it is decided by the smaller of the two windows, correct? So in this case, what is the smaller of the two windows? It's 1.76, right? So the maximum undistorted I sub c swing will be 1.76 milliamp. And then so the maximum undistorted output voltage swing is what? Because the output voltage is related to the current, right? So what was it? What was the formula? VO is equal to IC times what? 500, right? If you go back to your notes. So therefore, it's 1.76 milliamp times 500. So that's about equal to 0.8 volt peak. Is it? Yeah. All right. So let me give you one more question, and we can stop. So what happens if I have an input voltage that is equal to 10 millivolt? Let's say if V sub I equal to 10 times 10 to the minus 3 sine omega t. Then what is the waveform of the output terminal? Maybe I should say waveform. Why do people keep on sending me text? I should turn off the volume. Okay, so what is the waveform at the output terminal? Okay, you should know that the AC component of the output terminal is V sub I times A sub V overall. Yes? So therefore, A sub V overall is minus 20, right? So it's minus 20 times 10 times 10 to the minus 3 sine omega t. But this is only the AC component. There also is a DC component, right? So what is the DC component? What is the DC? This capital. Is that mine? So this is the capital means DC, right?
Yeah.
So what's the DC component? Well, we are talking about the voltage here, right?
Yeah.
DC. Is that the same as VCC minus VCEQ2? Is it? This voltage is VCC, right? And then this voltage is what? VCEQ2. So the rest of the voltage is V sub O, right? So therefore, it's 15 minus 13, right? I think, what was it 13 or something?
Yeah. Yeah.
Okay, so therefore it's 2 volts. Okay, so with that, you can go ahead, sketch the waveform at the output terminal. And you know, if you build an amplifier like this in the lab, and you put the probe at this terminal, and that is what you expect to see, right? Everything we do here should be consistent with the experiment. Huh? We're not doing this for nothing, you know. This has to be the same as what you could measure in the lab. Okay, so the output terminal, right? I have a 2 volt DC, and on top of that, I have a 0.2. You see 0.2? 0.2 volt, right? Peak. So this is the input, yes. This is the V sub I, and the peak was how much? Was 10 millivolt, right? That's V sub I. For V sub O, first of all, you should know there's a phase shift, right? Why? Because it's a minus sign, right? So therefore, if this is positive cycle, this will go to what? Negative, right? Oh my goodness.
It's coming.
Now, the frequency, I did not do a good job, right? But the frequency should be the same, okay? There's no change. But the cycle, yeah, it's inverted by 180 degrees. Okay, then what is the maximum peak, according to what I have? Is, no, right here. So it's a 0.2, right? So the difference here is 0.2. So therefore, this one should be 2.2 volt. This one should be how much?
1.8.
1.8 volt. Huh? See, we have done all the numbers, but we have to make sense of all the numbers. And that's what it is. How much time I spent on this example? An hour. An hour, we have an hour and 15 minutes.
Are we doing just one question on the exam?
Yeah, I mean, that was one of the exam problems.
Is that the only one? Because that's all we have time
Yeah,
for.
just one.
Just one problem? All right.
And remember, I had to stop and explain to you. You don't have to. So you can supposedly do quicker. Huh?
We don't have the experience that you do.
That's why you need to
You've done this
exercise. All right, so let me give you some insight about the exam. It will be one problem with multiple parts. Okay. The problem will be, of course, it will be a bipolar circuit. Huh? There are two possibilities. You can see a single stage. You can see a multiple stage. I know you like single stage. But believe me, it doesn't matter which one, the difficulty will be about the same. Okay? Because I've done this many years. So I can, if I give you a multiple stage, I can try to make it simpler. If I give you a single stage, I could make it a little more difficult. Okay? But you can see that even it's a multiple stage, the concept, right? There's no difference, right? Anything else you want to know? Yeah.
Would this example count as a simple multi-stage, or?
This one? I think if you understand the concept, it's not that difficult.
I understand. There's a lot going on.
Yeah. Actually, the more difficult part for me is just the algebra.
Right.
Right? Because there are so many equations you have to try to manipulate the equations. As far as the concept is concerned, to me, it's quite simple. I hope that's the same for you. Okay? Yeah.
So what are the biggest things that students always mess up on? Like what are the traps we need to watch out for?
Oh, that's the short.
Yeah.
Besides the shorting, the shorting capacitor, but like what else?
Okay. In the past, most of the students did correctly on the DC analysis.
Oh, yeah.
Yeah, right. It is very simple. Okay. But when they get to the AC, sometimes they will make mistake right here. Okay. And as I said, that's a major mistake. Once you have made a mistake here, you are probably below average.
But if most do it.
Yeah, I'm not kidding. Because if you make a mistake here, everything is wrong. I don't know how to give you partial credit. Okay, now if you make a right mistake, if you make it correctly here, then the rest of it, people make just, yeah, algebra. Some mistake in algebra, calculations. That's minor. That's minor. Okay. Then people also make mistake on the plot, on the AC and DC low lines. A common mistake I have found in the past was that, I always ask for AC and DC low line. Okay, trust me, you can see that the same, right? Doesn't matter what circuit you can see. And sometimes the student do not give me enough details. They just draw two lines. That's it. I'm not going to take that, right? Because when you have two lines, I need the boundary conditions on both lines. I need to know the slope. I need to know the Q point. Got it? If you don't give me these details, I have to take out some points. Reasonable, right? You cannot just draw two lines. Again, I want to emphasize that you should try to understand the concept, okay? Nothing to memorize. If you do need to have some equation, you can write down on a piece of paper. As you can see, when I did my example, I remember all the formulas. They are not so difficult.
I have more of a conceptual question. So in this problem, you assume that R of pi was very, very small.
Yeah.
But in previous chapters, we've assumed things about R7n being equal to like 0.1 times beta plus 1.
That's different.
Why does that not apply?
No. That condition applies to a special case called bias stable circuit. If in the problem you see, say, design a bias stable circuit, then you can use that condition. Otherwise, you cannot. Okay. Now, if you do a problem like this and you see this equation, right, like here, then you can assume that.
Okay.
Yeah. Can I explain what this one?
Yeah, I just wanted to know how you get RE.
Oh, because if you assume this is smaller than that, you can drop it. If you drop it, there's only one unknown in the equation.
Okay, we know I can get one.
Yeah, but as I said, you need to go back and verify this assumption. I did not do that. I should, right?
Yeah,
so what was so you have to try to calculate R pi 1, okay? And in order to do that, you need to know what is ICQ1, correct? So you calculate that and try to find out if this is correct. 99% is correct. I don't know if I have anything else to tell you. Yeah. Huh?
On some of the homework, the biasing of the transistors was reversed, and the current was leaving the collector instead of the emitter. Do you expect to see anything like that?
Which one?
Like a couple of the homework problems have to leave the collector, but the current going inside the transistor instead of following the emitter current.
You mean the collector current go inside?
That was kind of reversed bias.
That's a PMD. Yeah. As I said in the beginning of this subject, we are not going to cover any PMD.
Okay.
And I don't think any of the homework problem I gave you has PMD.
One of them was.
There was one? Yeah. Oh, then I made a mistake. I should not give you that type of problem.
Going into it, I can't remember.
Yeah, that's a PMD. That's a PMD. Yeah. No. But I will post the solution this afternoon. Okay, so you have enough time to study. Okay, study. Don't go anywhere. Okay.